This video visualizes the data taken in a hyperspectral PIFM image. All the data in this video is taken from a single image. At every pixel, the tip pauses and PIFM is recorded as the excitation laser is swept from 1300 to 1700 wave numbers. Each spectrum is recorded in 400 milliseconds, and one from a single pixel in the image is displayed here. These reference spectra show similar measurements on homopolymer samples. The blue line is the signal for P2VP, and the red line is the signal for PS. A slice of the spectrum about 10 wave numbers wide is selected, and this image shows how strong the PIFM signal integrated over that range is at every pixel. In this video, we will run the selection from left to right and show how the PIFM signal identifies the different components of the sample by their absorption peaks. In this first 100 wave numbers, nothing absorbs strongly, and we see no contrast in the PIFM image. Here is the first P2VP absorption peak. In the image, the P2VP regions become brighter. At 1569, there was another weaker P2VP peak. And now another region of low absorption. At 1492, we have the first PS peak. And P2VP at 1470. At 1460, PS and P2VP are both low, but a third component, a contaminant, is highlighted. 1450 is another PS peak. And 1444 is right between a PS and P2VP peak, where the absorptions of the two materials are roughly equal, but the contaminant's PIFM signal is much stronger. 1438 is the last P2VP peak. Let's take one more look at the prominent peaks. Here is PS highlighted at 1492. If we draw some lines on the image where the PS is bright, and then switch to the P2VP peak at 1470, you can see that the bright and dark regions have flipped, showing that we are identifying the two components. If we circle the regions that we identified as contaminants and investigate their PIFM signal at several wavelengths, we can show that they must be composed of a third component. At 1589, they are slightly darker than the P2VP. At 1470, they are brighter than the P2VP. At 1492, they are darker than the PS. And at 1450, they are brighter than the PS. The hyperspectral image shows that these contaminants have a separate absorption spectrum which matches neither the PS nor the P2VP. So far, we have considered only the hyperspectral PIFM channel. Let's take a look at the topography and phase, which are being obtained simultaneously. The defects are clearly visible in topography as 1 or 2 nanometer bumps, and they also appear as negative shifts in the phase. The topography does not clearly show the fingerprint pattern, but it is perceptible in the phase, though the contrast is not good. If we draw some lines on the PIFM and phase images, the PIFM shows us that the positive shifts in the phase correspond with P2VP. This image is 500 nanometers wide by 250 nanometers tall. The PS and P2VP lines are each 20 nanometers wide, which means that we are resolving features about 1/350th as long as the excitation laser's wavelength.